This video is on constant force work. That is, the work done when the force remains constant. In general, the equation for work looks like this. That equation simplifies if the force is constant. If the force is constant, you might remember that whenever we integrate things, if you have a constant, you can pull that outside the integral. If we do that here, then we are simply integrating all of these little tiny displacements. And when you integrate each tiny displacement, you get just the total displacement. We could put a d here as well if we want, f times d, an s, sometimes that's used. That's what we're dealing with here. So let's figure out what type of work is being done for each of the cases shown here. To help with this, I'm going to take that force and I'm going to break it into its two components, one of which is parallel to the displacement and one of which is perpendicular to the displacement. So if I take this component that is parallel to the displacement, that one right there, and then the component of the force that is perpendicular would look like that. So that's going to be positive work because that force component, shall I call it F parallel, is parallel. Those two vectors are pointing in the same direction. How about this next one? What's the component of F that is parallel to S? Right there. The one that is perpendicular is right there. And so here again, this is going to be positive work. The component of force that is parallel with S is in fact parallel and not anti-parallel. If I take this force and I break it into its component that is parallel to S and perpendicular to S, you can see that here the component of F that lines up with the displacement is in the opposite direction. So this is going to be negative work. And what about in this last case? The component of F that is parallel to the displacement looks like that. The component of F that is perpendicular to this displacement looks like that. The force, the component of force that is perpendicular, we're not at all concerned about that when we're finding work. Similarly over here, I could put X's through those green components because if you take that component multiplied by the displacement, you're going to get 0 because anytime you take the dot product of two vectors that are perpendicular, you get an answer of 0. So these two show us that we're going to get a negative value for work there. We mentioned just a bit ago that 0 work is done whenever F and the displacement are perpendicular. There's no work done. The dot product of two vectors that are perpendicular is 0. And this is always the case for what type of force? A centripetal force. And the reason for that is that a centripetal force is always perpendicular to every tiny little displacement. When you have a centripetal force, it's because you have a particle that is going in a curved path like this, and a centripetal force will always act towards the center. So there's your centripetal force right there. The velocity is always tangent to that path. And what about the little tiny displacement? The little tiny displacement, I'll draw it bigger, of course, than it really is, but that little tiny displacement right there is parallel to V. So there's dx right there. And he's always perpendicular to that centripetal force. So a centripetal force can never do work on an object. Centripetal forces do 0 work. They change the direction, but they never do work.